Hey everyone, I'm super stoked and honored to have received an invitation from IPS to do today's presentation. I'm really excited about it. So, the subject of my presentation is the utilization of registered IPS to accelerate the deployment on the SOLEX platform for large-scale models and enhance the efficiency of the process. Before we start sharing this share, let me introduce our SOLEX platform. The platform we offer is known as Bento Cloud, which is part of our Solex solution. Before I delve into our local cloud, I would like to provide an introduction to our local ML capabilities. In fact, local cloud is a project of local ML, and local ML is a Python library, or you can even designate it as a Python SDK. Its main responsibility is to aid developers in constructing AI applications with large models more easily and efficiently, providing them with a convenient and user-friendly framework. What are some of the advantages of using it? The main advantage is that it is a highly integrated software development kit, SDK, for parsing. Our SDK is designed to be simple and user-friendly, making it easy for developers to create applications. It allows developers to utilize standalone models, similar to standalone applications, enhancing flexibility and efficiency in development. But the way you deploy it is in a distributed manner, so its development model is relatively simple. It can develop a high-performance AI application with a low burden on resources, which makes it efficient and resource-friendly. Another advantage is that it is capable of providing support for different frameworks like PRTouch, TensorFlow, PRTensor, and more. It has the ability to support various models in different frameworks, making it a versatile and flexible tool for machine learning applications. So it is a completely unrelated thing to framework, but it is like a very low-level software development kit, specifically designed for creating prototypes. Then Bento markup language constructs a product, which we commonly refer to as Bento during the process of development. Bento can be viewed as a Docker image, which is a product that provides healing capabilities for Docker. It's the basic unit we deploy. This Bento can be deployed in your local environment. You can deploy it on EC2, or AWS Lambda, or AWS SageMaker, Spark, Kabuka, etc. Of course, it can also be deployed in Kubernetes, or any other suitable platform that meets your requirements. It is analogous to when a developer finalizes the development of a bundle, they have the ability to conveniently hand it over to other users, who can then effortlessly run it and successfully reproduce the developer's runtime conditions, ensuring accurate execution of the software in the same environment as intended by the developer. So it takes care of a few dependencies, manages a few models, and handles various static files in order to ensure smooth operation. So the architecture of Ubuntu is like this. It will include several models, and then include some Python code from the developer. And within this parsing code, it will have several types of logic. There are some pre-processing logic, for instance, when a user's request comes in, it needs to be processed in advance. For instance, if the user sends a picture, they may need to perform a series of quantization operations on the picture. Then there will be some business logic, as well as some of our own business logic. It will also automatically inherit some code for observability and monitoring, which is actually for developers. Assisting our SDK automatically is aiding him in achieving it, and initially our main goal is to specifically serve certain traditional AI models in order to ensure their successful implementation. However, as we are all aware, in the previous year or two, significant language models have begun to emerge. Thus, TLBT's application, and subsequently our foundation, can also cater to the large-scale models, which are known as LLM models. There exist some minor disparities in their architectures. In order to support these large models, we require optimized engines such as VLM, which can be seamlessly integrated. Then, taking it a step further, we abstracted out the concepts of API server and render, elevating it to a higher level of abstraction. API server is essentially comparable to an ingress for a service, an entrance for a service, and then render it is different specific business logic. For example, a certain render employs an image processing model, and a runner employs a text processing model in order to fulfill its designated tasks. Certain runners may possess their own skinny code, similar to this runner who opines that utilizing Python for handling specific business logic might result in slower performance, due to Python being more suited for Internet of Things (IoT) type of logic. When you require CPU-intensive logic in your code, you have the option to utilize programming languages that are more conducive to CPU-intensive applications, like Rust, C++, and others, for developing a custom renderer. Additionally, you have the capability to deploy it within our bundle. Yes, this is the entire structure of our bundle. By using this framework, we are able to see that our bundle has the capability to integrate multiple models inside it. This indicates that our framework inherently includes certain functionalities for managing multiple models effectively and efficiently. Alright, when dealing with large models, the crucial factor to consider is that our API server also provides server-sent events, SSE support, because for large models, the response time can be significantly slower. Typically, we utilize a flowing response to enhance the user experience, so we have incorporated support for server-sent events, SSE, which serves as the foundation of our architecture. Now, allow me to introduce Bento Cloud. As the name suggests, Bento Cloud is a platform that allows Bento to be deployed on the cloud. First of all, it is a Solaris platform, specifically a native Solaris platform based on Kubernetes. It naturally brings these three benefits. First, it efficiently utilizes some scalable infrastructure. Another benefit is that its deployment is completely independent of your infrastructure dependencies. It is decoupled and detached. Additionally, it provides these advantages and contributes to the overall efficiency of your operations. An additional benefit is that it has the capability to automatically manage certain hardware resources, which is the reason it achieves some of Solaris's effects, thus enabling users to leverage this platform. They are highly frugal and penny pinching. In simple terms, it means that if their services are not requested or sought after, they save money. The quantity of copies they possess can be zero. When a request comes in, the copies commence deployment, and then they initiate the utilization of hardware resources. This triggers a sequence of hardware consumption, thereby enabling significant cost savings for users on our platform. This is the overall architecture of our local cloud. It includes three important stages. The first stage is the development stage. During development, when you use our local ML development to create a project, the resulting product is called a bundle. But where should you store this bundle? Just store it in our bundle cloud, which means that at this stage, the role of bundle cloud is like a registry for bundles. It can be compared to a registry for Docker images. If you compare the bundle to a Docker image, then in the second phase, it's another integration phase. The integration phase means that if you want to deploy the bundle to a cloud environment, you need an OCI image, also known as a Docker image. In this stage, we have a component called Asia Pacific Image Builder. Why Asia Pacific? Let me explain. It's based on our original open source version, or what we call the production version, named Asia Pacific. So we refer to it as Asia Pacific here. The component is shared between our open source version and our SaaS version, so it's called Asia Pacific Image Builder. It builds the local image into an OCI image for future applications. Then we reach the third stage, the deployment phase. During deployment, we also have a new component called Yata Serverless, responsible for deploying OCI images generated in the previous phase to Kubernetes. It's a straightforward process with 3 steps, and Bundle Cloud covers all 3 steps. Today, our discussion focuses on the third phase of the deployment. In this deployment phase, the main component is the Asia Pacific Solace. Let me briefly introduce the architecture of Asia Pacific Solace. Of course, this may not be the main focus of today's presentation, but it will give everyone a basic understanding of Asia Pacific Solace. How does Asia Pacific Solace manage to scan from the server? So when a request is made, we have an interceptor that intercepts the request and puts it into queue. Then, utilizing a component from Kodak Cloud, we are able to perform scanning services by leveraging the advanced scanning capabilities of the cloud-based technology provided by Kodak Cloud Services. It will create an HPA, and then it will also go to our external service orchestration system, XSOS, to fetch some metrics. This scanner will return some metrics when there are values in this queue. The system will inform you to go scanning up, indicating the necessity of scanning up the replica of the application. Afterwards, this replica will contain a proxy server card within the pod, enabling the scanning process to take place. It is accountable for consuming the requests in this queue and dispatching the consumed requests to the actual container in our application for processing, where the genuine users are present. Finally, let's go back and give a brief introduction of our entire simple architecture. Next, let's talk about the challenges. Yes, and then with the arrival of this large model, challenges arise. First of all, for a platform, the time required to start is crucial. Just imagine if a request comes in and your replica starts from scratch, and if the time it takes to increase exceeds a certain duration, let's say 5 minutes, it could have a significant impact on the overall performance and user experience of the system. This request is likely to have been considered a timeout in some previous HTTP technical settings. Yes, this is a terrible situation for user experience, especially for large language models. Due to the large size of the model file for large language models, typically tens of gigabytes or even 20 gigabytes, it will result in a significantly prolonged stage when initializing your pod and downloading the model. As a result, the time required for your cold start will be greatly extended. Yeah, another challenge is the consistency of your data, which is something that is unique and specific to the serverless native platform. We have faced certain challenges, but we have effectively addressed and resolved them through our meticulous modeling of local reducers on this platform. And then there are certain considerations with respect to data security, which is the reason why there is a requirement to deploy the primary model to the cloud. This is because OpenAI, which is also significant, must provide certain APIs for users to utilize. Including some large-scale models in our country, it also needs to provide us with some APIs to use. However, its application limitation is the security restriction, because many enterprises or application scenarios have particularly high requirements for data security. It is not possible to pass this sensitive data to a third-party API for processing. Therefore, it wants to deploy the large language model on its own cloud and handle these data by itself. This is also the significance of the existence of our cloud-based platform for this substantial language model. So then there are 3 challenges, and today the primary challenge we need to address is this code start time, which is also a proposal that we have successfully managed to reduce the cold start time with the assistance of 30 seconds, as per the help provided. So looking ahead, our main focus and priority will be on introducing and emphasizing this crucial aspect of cost time. First, let's have a conversation about why the cold start time of large language models is exceptionally slow and time-consuming. To begin with, the reason is that in our typical scenario, we normally include the model file as a component of the container image and incorporate it into the container image. Subsequently, during deployment, you initiate the retrieval of this container image and commence the process. This retrieval procedure is frequently quite time-consuming due to the typically sluggish nature of the registry. This is the architecture we just started with. Basically, initially, we'll package all the files, model files, Python code, Python dependencies, and even CUDA into a container image. Then you can execute this container image in Kubernetes, but you will encounter multiple challenges in this process. The initial one is the downloading. Despite the fact that you can acquire this container image, each layer of your container image is downloaded in a fixed manner, but when you decompress it, it is done in a serial manner. When it decompresses to the layer that contains a large number of models, it will accumulate and occupy a large amount of CPU time. And there is another challenge for everyone to think about. When you employ the same model in different locales, for example, all locales utilize the Llama TD model, but for this architecture, it will result in wasting 2 identical spaces, both of which will be packed into different images, exist as separate layers, and will be downloaded and decompressed twice, leading to a huge waste of resources. Therefore, this particular architecture is incapable of sharing models. So allow me to provide an explanation on why we selected JuiceFS as the solution to address this specific problem. Initially opt for JuiceFS. We primarily take into account 3 benefits of JuiceFS. The initial one is that it is a POSIX protocol, thus it is extremely straightforward. You do not need to wrap it again, and then abstract it into a POSIX protocol using Fuse, and enable our containers applications to read it. So on one hand, it is a very simple process. On the other hand, it possesses a very high throughput, which means it can come close to utilizing the entire bandwidth of S3 or GCS when performing downloads, thereby maximizing efficiency and optimizing data transfer. The third one is the one we just mentioned. It can share the model very well. When we store the model separately in the menu, different branches can share the same large reservation model. And then this is us. This architecture is used when we create container images, where we isolate our models and place them in a designated storage. This storage is referred to as storage in this context. It is also worth mentioning that the container image exclusively consists of my Python code, Python dependencies, and a few essential environment dependencies. The advantages of this approach are quite apparent. In essence, you have the option to download your model and layer at the same time, without the need to unzip your model. For instance, the process of unzipping your image layer will be incredibly fast and efficient, ensuring a seamless experience. Another important aspect is that the amount of data you download will be very small, and the bandwidth of our container registry is significantly smaller than that of blob storage. So this will greatly enhance download performance and improve the overall efficiency of the system. Another thing is that we have made the granularity of the entire cache finer. Previously, the cache granularity was at a certain layer. Now, even a specific model has its own cache granularity. Additionally, when it comes to registering FS for certain sizable files, it will divide them into smaller parts, and then it is capable of achieving streaming for a model, which is comparable to a streaming read or streaming load. It is similar to the capability of loading models one by one, and during this loading process, we are also able to download our container image simultaneously. Furthermore, we make use of GKE's image streaming technology, which enhances the efficiency of the overall process. In essence, we have two streaming processes happening, model streaming and image streaming. They both fetch data at the same time in order to decrease the startup time and make it more efficient. However, we also encountered several challenges when integrating FNS. This specific challenge is actually the first one, and the second challenge is actually a more common one. When any already mature platform introduces a new component, they will inevitably encounter these challenges. It is inevitable to come across these challenges whenever a well-established platform incorporates a new component. So how can this component operate flawlessly in conjunction with our current components and observe their behavior accurately? And secondly, when you introduce this new component, what kind of modifications will it bring about, and how will it impact the overall system and its functionality? Another change, meaning the previous bundles container images included the model, but the later bundles container image no longer includes the model. However, how can you make the container images of these two kinds of bundle compatible so that when we deploy our Solaris platform, they can be mutually compatible? This is a compatibility issue that you need to consider in your code. The last one is a problem we found during registration testing. It's an interesting problem that should be addressed. Take it into account in your code implementation. When you utilize registration to download models, it will be notably slower in comparison to downloading directly from the mirror. What is the reason for this? Then we proceeded, and our classmates assisted us in identifying the issue. We discovered that we were utilizing a network disk as a cache disk on the iPhone. However, the bandwidth of the network disk is extremely limited, which ultimately results in an unusual phenomenon. When we do not access the cache, it will be slightly faster. However, once we access the cache, it becomes significantly slower. Therefore, to resolve this problem, in reality, this is a relatively straightforward fix. We simply mounted some local MME SSD as a cache disk for this CFS, and that effectively and completely solves the problem we were facing. And then our next step is to do more observability, which is how to observe the entire architecture in a perfect running state, and then be able to locate and obtain some metrics, and then further optimize our configuration better trying to avoid the occurrence of the third situation again. And there is also something we need to do, which is probably doing some preheating and so on. Effectively utilize the built-in caching capabilities of these primary materials. For instance, once we have registered the model in MS, we can make use of it during the Chinese New Year period. In the cluster that handles business operations, we can proactively plant these models into the cache directory. This way, we can further improve cache hit rate and enhance our freezing time. All right, sure thing. So, this is the main thing I'll be talking about today.